Chapter 3 takes on the very intriguing topic of thermodynamics, and it relates thermodynamics to chemical reactions, which in the parlance of chemistry is called thermochemistry, and it's concerned with the relationship between energy, heat, and work. And the first aspect of the development of thermodynamics involves the first law of thermodynamics, which on the face of it is a statement of the conservation of energy. But developing the link between scientific concepts and the real-world context turns out that the first law of thermodynamics is the foundation upon which we build all of our understanding. And as we'll see, as we address more and more complex problems, the first thing you write down is the first law of thermodynamics. But the first law also informs us about something very important, and that is the energy flow through an economic structure. So let's take this very famous diagram from the Lawrence Livermore National Laboratory. And that diagram starts with the primary energy that goes into sustaining the social structure, the economic structure of, in this case, the United States, although there are tremendous examples in developing countries that mimic exactly what I'm going to describe here. So the primary energy input involves petroleum, it involves coal, it involves natural gas, it involves renewables such as solar and wind and nuclear, geothermal, and it tracks that primary energy through to electrical generation, but then also how that electrical generation in combination with that primary energy sustains residential, commercial, industrial, and the transportation sector. Now you can tell immediately when you look at this how efficient particular subunits of this structure are. Let's look at transportation. We've already talked about the fact that when an automobile converts the chemical energy in gasoline to motive force, the efficiency is very small. You see that because the flow of usable energy into the far right-hand part of the diagram tracks what's actually used to move trucks, buses, aircraft, and so on. But it also tracks the wasted energy that goes into the second category on the right-hand side. But remarkably, the rejected energy is the wasted energy. And in the U.S. structure, 67% or so of all the primary energy is wasted. Only about 33% goes to useful work. And so this particular diagram captures a huge amount of the macroscopically important aspects of thermodynamics. And the question is, why are carbon-based fuels inherently limited in their efficiency for producing mechanical work? Why are technology developments associated with converting, for example, photons to electrons through converting solar power through a photovoltaic to electricity? Why are those so efficient? Why are electric motors 95% efficient while gasoline engines are 15% efficient in converting the incoming energy to usable work or the execution of issues related to economic development? So let's take an example and work through this specifically. We're going to use this diagram to track this through from the origin of the energy to the production of light within the house. We start with 100 units of chemical energy contained in the coal. It's 38% efficient in converting chemical energy to electrical energy. That means the power plant loses 62 units of that original 100 units of chemical energy in the coal, and it's dumped as waste heat. So that provides us with 38 units of electrical energy that goes into the power grid, and the power grid transmits energy through to the local use at the house level or the factory or the school or whatever the building is. And that removes 2 units of energy. Now, it's true the technology of moving electricity around is improving dramatically. And you may have read about high voltage direct current distribution of energy at the national level. And it turns out you can transport electricity with a loss of just 1% per 1,000 kilometers of transit if it's properly designed. But in many systems, this is a reasonable approximation. So 2 units are lost. That means we have 36 units of electrical energy entering the house. Now we plug in the light bulb. We plug in the light bulb to create light that can be seen by human beings. But it turns out that only 2 units of that 100 units that originally came from coal actually goes into light that human beings can see. 34 units goes into heat. This is why light bulbs are so high temperature. You can't touch one after it's been running because of the very high temperature. And all of that energy goes out in the infrared, which heats up the bulb and the lantern around it and the air around it. Only 2 units can be seen by the human eye. Now this is why light-emitting diodes are such an important technology development, because they're some 10 times as efficient as an incandescent light bulb in converting electrical energy into light that can be seen by a human being. But thermodynamics also tells us something very important. We looked at the fact that when we combust gasoline in an engine, in a heat engine to drive an automobile, only 15% of that chemical energy comes out as useful work. But thermodynamics allows us to analyze this quantitatively. It allows us to look at this system as a high temperature reservoir, and in this case it's the high temperature created by the detonation of gasoline within the cylinder of the automobile. And the exhaust dumps heat out the cold reservoir, that is out the exhaust pipe, and the useful work comes out as the motive force driving that automobile. But the brilliant thing about thermodynamics, and the thing that makes it so interesting, is that you can actually calculate the efficiency of that heat engine. It's called the analysis through a Carnot cycle, or a Carnot efficiency. And again, the efficiency is defined the same way. It's the work produced divided by the heat in. That is, what you get, the work, divided by what you pay for, the gasoline that goes in to create that heat. And it turns out that we can calculate the theoretical efficiency of that heat engine using the analysis of the Carnot cycle. And not only does the Carnot cycle allow us to analyze why heat engines are so inefficient, it tells us very clearly how to make them more efficient. But the remarkable insight that comes from thermodynamics also applies to heat pumps. And this turns out to be a profoundly interesting aspect of the quantitative analysis of thermodynamics. Because we know what heat engines do. They drive automobiles. Heat pumps are of 2 particular types. One of them you're very familiar with. It's a refrigerator. So a refrigerator works by taking a cold reservoir that's inside the refrigerator, doing some work, driving that compressor that you can hear turn on, and moving heat to a high temperature reservoir. That's why the back of a refrigerator is much warmer than the room around it. It is extracting heat from inside the refrigerator and dumping it into the room. But there's an important global context to this, and that is the heat pump, because I could consider outside air as one reservoir and inside air as a second reservoir. That is, I could take a day at 0 Celsius, that's the freezing point of water, and to us that's very cold. We want a room that's 20 degrees Celsius, room temperature, and the heat pump tells us exactly how to do that thermodynamically. And it turns out that heat pumps are so efficient that they'll take 1 unit of electrical energy and produce 5 units of heat into the house. That means it's much more efficient to burn natural gas in an electricity generating power plant and to drive a heat pump to your house. That's much more efficient than burning natural gas in your basement. And this is one of the remarkable lessons from thermodynamics, and it comes quite directly from the fact that nature looks at temperature from 0 degrees Kelvin. 0 degrees Celsius is 273 degrees Kelvin, and the room temperature, just 20 degrees Celsius, is 293 degrees Kelvin. So all that heat pump has to do is make up that tiny difference in the kinetic energy intrinsic to that air, and you have a warm room with remarkable efficiency. And when you look at the capability of heat pumps for solving the global energy problem, it's a remarkable contribution, and its understanding comes directly from thermodynamics. Finally, one other aspect of thermodynamics is that it allows us to understand what's happening to the climate structure. And one of the most profound changes in the global structure is in the Arctic. And in the Arctic, 75% of the permanent ice has disappeared in the last 35 years. This is a stunning change. In 1979, there were 17,000 cubic kilometers of floating ice in the Arctic at the end of the melt season. That occurs in the middle of September each year. And by tracking this volume of ice over the past 3+ decades, it's now dropped to 3,000 cubic kilometers of permanent ice at the end of each melt season. 75% of that original ice is gone in 35 years. But notice something else. The curvature in this plot means that as ice disappears, the rate at which it disappears increases. And that's caused by feedbacks in the structure of the climate system. And it doesn't take a complicated model to realize that by 2025, there'll be virtually no permanent ice left in the Arctic. And this is all thermodynamics, because we can calculate the heat Q that goes in to the observed disappearance of that ice structure. And we can also analyze the mechanisms and realize that there's no mechanism for extracting that heat. That heat that's gone in has permanently removed that ice. There is no known mechanism that can counter that. There's no known mechanism for extracting heat from the Arctic, so there's no known mechanism for stabilizing the climate structure that depends on the existence of permanent ice in the Arctic.